Hey everyone, Rob here. I wanted to do a quick video about the unified clock system and frequency lock loop for the MSP430 F5 and 6X series chips. It's a little bit confusing, so I was going to try to maybe just make it a little bit easier, go through some of this code. I think it might help a lot of people out. So this is just a program as an example, and most of the time we use this function in FFL settle, and you pass in a frequency and a ratio. So I passed in this, which is the main clock frequency I want, basically the DCO output frequency I want, divided by 1,000, because the function requires you to divide it. If your clock frequency is in megahertz, it requires you to divide that by 1,000, and this is a ratio. And so we're going to go through this function, and hopefully it'll be pretty quick, and we'll see how all this works. So the first thing you want to do is get the data sheet for the UCS, Unified Clock System. So this is a clock system for the MSP, and I'm using a 5637 part. And the very first thing you need to do is read this whole thing, and then read all the registers. And so after you do that, there's this diagram that kind of shows you how this works, and this is actually extremely valuable. Like, if you get stuck, check this out, and things will probably make a little more sense after you really understand how this works. And so the FFL block is the frequency lock loop, and this is what you use to set your DCO clock frequency. And the DCO is a digitally controlled oscillator that generates your clock, your high-speed clock for your system. So in other parts you'd set this as close as you can, but the FFL block is basically like a feedback loop that continuously reconfigures this to keep it as accurate as it can, or as close to the required frequency as it can. So the way this works is you have the DCO modulator, and you configure it with its bits. If you're not familiar with the DCO, you should go study that and then come back to this, because I don't cover the DCO. If there's enough interest, I could do a video on it, but you just have to let me know. But this is your main clock output, and you're going to configure this. Well, with the FFL, you can let the FFL configure it. And so if you look at this, this is an input. FFL ref clock is a reference clock input to this frequency lock loop, and DCO and DCO clock div are the outputs. And so what you do is you select your reference clock with this mux, and it'll pass in some reference clock. So for me, I've configured my reference clock to be the REFO. It's a 32 kilohertz, 32768 clock. And so if you look at this bit 02, you can see I selected that, which is coming out of here, down here, and in here, and there's 2. And so that's my reference clock. I have no division, so it's going to come in, this clock's going to be 32768 hertz coming into this positive terminal of this frequency integrator. And this is the feedback. This is the reference clock. This is the feedback system of your FFL. And so the way this works is you have a reference clock, and then you take the DCO clock output, which we'll say is 48 megahertz or something, and you divide it down so that it matches the reference clock. And so this integrator is just kind of like an op amp, where it tries to match the 2 inputs, and you feed the output back into the input. And the clock divide here is just the DCO clock signal after it goes through this first prescaler. So to configure this FFL system, really what you need to look at is your reference clock divisions, which I'm not going to use in this example, but you could divide this clock to make it even slower, which would mean you'd want to divide this DCO output feedback more to make them match. So I've got 32K coming in here, so I need to see 32K over here. And so what happens is this integrator configures this DCO modulator to have a clock output that matches this positive clock input after it goes through these dividers. So that's kind of just the general idea of this, how this works. You got your high frequency crystal, and then you've got your oscillator, and that's like XT1. But so we'll look at this function because that FFL settle function configures this. And so we'll go through how that works now. So first what we're going to do is look at our parameters. Like I said earlier, I'm going to configure this for 20 megahertz. I want a 20 megahertz DCO clock for my main clock and my sub-main clock. And so we're going to use this function to configure that for us. Pass it the 20 megahertz that I want. If you control click, you can see this is defined as 20 megahertz. And then divide that by 1,000 for this function. And because that's just what it expects. You'll see when we get into the function. And then this ratio is gonna be a number that represents the divisions that you need. So you're going to divide the clock you want by your reference clock. And that ratio, if you go back here, DCO is the clock that you want, and your reference clock is the clock that you have to match. And so the ratio is going to be this prescaler and this prescaler. And so the way this works is this prescaler is 10 bits, so it can hold a value up to 512. And so if the DCO is 512 times faster than your reference clock, then you can load this at 512, and it will divide this DCO output by 512, and these will be a perfect match. So the integrator will constantly output a DCO frequency that this is just, we'll say this is just 1, and then this is 512, and so it'll constantly output a DCO frequency that's 512 times this 32 kilohertz, because after this DCO clock comes in here, it gets divided by 512, it's now the same 32,768 hertz signal. And if we divide this feedback signal anymore and make it slower, this DCO is going to have to output a faster signal so that this feedback loop, it can overcome the larger and larger dividers and match this. So this is constant, and this is your feedback input from your DCO modulator that's configured by your 10-bit frequency integrator. And so that's the idea. So we'll get into this code and finish up this video. So again, control click, and if you look at this, it has the real functions here. This is just to take care of a delay. So you got your frequencies of your system that you want, which we want 20 megahertz. Divide that by 1,000, that's what this number is. And then your ratio, which is, the ratio represents this divider and this divider. And if you think about it, if this divider has to be more than 512, then you basically overflow into FFLD, which will divide this signal by 2, and now you go back and see what you need to set this to even out your signal. So for example, if we had to divide this by, if this was 32,768 and this was outputting, we wanted it to be 800 times 32,768, then we need to divide this by, then we go over here, we look, 800 is greater than 500, so we're going to overflow. We'll divide this by 2, we'll set this to 2. Now our DCO clock after the prescaler is only 400 times faster than our reference clock, and then we can load 400 in here. So this is, think about this as kind of an overflow for this FFLN divider. This N+1 is your higher resolution division, and this is just a 3-bit basically binary power of 2 divider, just like normal clock dividers. And so you basically tune this up so that you keep dividing by more and more and more until you get under 512. And once you're under 512, you can then set this to that number, and it'll divide the signal out the rest of the way to be even to your reference clock. So there is one note in here. If you this first function is used because there's a delay requirement. If I can find it, that says you need to let the clock settle. Let's see, where's that? Okay, here it is. And so, again, you reading through the data sheet is the most important thing, but read through this. And it says, required between taps. So worst case, that many cycles for the DCO to settle. And so, when you reconfigure the DCO clock system, you want a delay of that much, right, to let it settle. And so 32 times 32 times n, and n says defined as FFL reference division. So you go back for this example, I'm not going to divide the reference clock by anything. So since this is 1, n's 1, so you have 32 times 32. So what they do is basically take this ratio, multiply it by 32, and that's x, and then you multiply that by another 30 because you loop 30 times, and that's your delay. So that's your system delay to let the frequency lock loop clock system settle. But the real function of interest is in here, in it FFL. So you can do this by hand by setting the registers, or you can use this function. It's a lot easier to use this function, so I'd recommend that. So it takes the frequency of your clock system divided by 1,000, so that's 20 million divided by 1,000 for this example, and then it takes a ratio, which is the ratio of your clock system over your reference clock, so that's 20 million divided by 32,768. So you go in here, this is just another thing in the data sheet it requires you to do, or at least is recommended. So you disable the FFL while you configure it. You set your ratio to D, and this is just so you don't overwrite your ratio because it'll work with D, and you'll see there's an instruction that actually changes D in the instruction. And then DCO division bits is the FFLD. And so this is the first divider right here, this prescaler. That's the overflow, remember? And D is actually going to hold the value for this FFLN, the n plus 1. And so if D is less than 512, we can just load D into FFLN, leave this as 1, and we'll get our division. Our division will be correct to match these two clock inputs, which means that the DCO output will just be FFLN times this reference clock input. If we don't use this, whatever number we load in this to match them means that DCO clock is that many times faster than reference clock. So for our case, that's not going to happen, and we'll step through this code to see how this works. Let's see. So go into debug mode and actually see this work. Okay, so step in here. Alright, run. Okay, so now we've run through our main program, through all this stuff. We've entered this function. And so let's look at what we're going to pass it really quick. We want a 20 megahertz clock frequency, and our reference clock is 32,768. Divide that, so 610. So now we go in here. Now we go in. Where is it? Go in, I think it's in the HAL. Yeah. Okay, so we go in here. So now we're in here. We've passed our two values, F system which here, see 20 million divided by 1,000, so that's 20,000, and then 610, which matches our 610 ratio that we calculated with the calculator. So now D is 610. Alright, so the first thing it does is check, is a frequency system above 16 megahertz? And if it is, it checks this because, well, one reason it sets a mode down here, and if it is greater than 16 megahertz, this sets our main clock to DCO and our sub-main to DCO. If it's less than 16 megahertz, it selects our main clock to DCO div and sub-main to DCO div, which, go back and look at the diagram. If it's less than 16 megahertz, then our main clock, which is going to be selected over here with these multiplexers. This is a clock bus, and so auxiliary clock, main clock. So if we're greater than 16 megahertz, we use this output directly from the DCO modulator, which is going to be our high-speed clock, right? So we're going to set that for main clock and sub-main clock. That's what this does. And if it's less than 16 megahertz, this clock div is this clock division signal. So we set our sub-main down here and our main clock here. We set that to the DCO clock signal after the prescaler, which is this line. So 3, 3. And that's what the mode bit's used for in this if statement. And we also, there's the mode, so since we're greater than, we're going to step into that. Let's see, we'll set mode equal to 1. See, we're greater than 16 megahertz, 20 megahertz. So now what we're going to also do is divide D by 2. And we divide D by 2 because we set the frequency lock loop FFLD divider automatically to 2. And so what that means is FFLD is going to be 2. So we set the FFLD register to 2, so we're going to divide by 2. So right now, the way this is configured is the reference clock is 32,768 divided by 1, and our DCO output, we're going to set our prescaler to 2, right, and save that off in D. So if we step through this, you'll see we right shift D to the 1, and this is short notation for D equals D to the 1. That's what that notation is. It's just a shorthand way of doing it. We set mode 0, step over that, it's 1. Okay, now this, the way this works is it checks to see if D is greater than 512. Alright, if D is greater than 512, we set DCO div bits, which is up here. It's already set to 2. We set it equal to itself plus 1. So you can see in the next higher level of division. So what that's doing is checking if this is greater than 512, let's overflow, increment this to divide by the next highest value, which should be 4. Then we're going to divide D by 2, right? Because basically what we're doing is we're adding a division by 2 here, and so now we'll divide this number by 2, because this number, now that the signal coming into this FFLN divider is half as fast, we need to divide this by 2 to keep everything equal. So overflow, add 1 to here, divide this by 2, and then check it and see if it's still above 512. And effectively what you do in that while loop is you keep dividing this by 2 and multiplying this prescaler by 2. That's what you're doing. So you're shifting the division. If it's too big of a number for this to divide, you're shifting the division down to this prescaler and dividing the signal by 2 by a factor of 2 every time. So divide by 1 first, then 2, and automatically gets set to 2 here, right? And then when you get in here, it divides this by 2 to keep them matched. So then we check again, divide this by 2. So you can see right now our ratio is 305. So D is 305. So D is not greater then 512. So that means, if for example, we're dividing this by 2, we put 305 in here. So we're going to skip this loop. Alright, so now here we're going to actually configure the DCO. And so when we configure the DCO, you set this to 0 to set the DCO on the lowest tab. What that means is if you go into, and it actually, okay, so if you get the part specific data sheet, this is the family data sheet that we've been looking at. The part specific data sheet. You go over here to DCO frequency. These taps are these slash lines, and when you configure this, you want to put it on the lowest setting, just so you don't overdrive the clock system. And so that's what we're doing here. We're clearing the control 0 register. And the control 0 register is, if we look at the register map, this is the register map. Unified control 0, unified clock system, UCS 0, and let's see. We set this to all zeros. So we reset this thing. So DCO tap selection. And it's going to be reconfigured by the FFL once it gets going, but we're going to kind of, I guess you can think of it as preset this. So that's, I set that to 0. Reset FN bits. This is going to be the control register 2, so let's check that out. For the sake of this example, it's 1. I'm going to set all this to 0. Right, 3FF knotted, which is and equals 3FF, that's going to be 0. So we'll set all this equal to 0. So the FFL loop divider is going to be cleared as well. All this can be cleared. And this is just to reset these registers so we can then configure them. So now here's where we configure our FFL division. We've got DCO division bits and D. And so remember, DCO division bits is, go back to the diagram, is DCO division bits, that's this prescaler, and D is this value. So really this whole function is just trying to figure out how to load these two dividers, the prescaler and the n+1 divider. So the DCO div bits is our prescaler, and if you look over here, DCO div bits is set to 1, 0, 0, 0. And the reason that it's set to that is, remember, we loaded it with this pound define FFLD, and if you look at this, this is set to 1, 0, 0, 0. And if we look at the register for this, registers CS2, you'll see this is the loop divider, and this is the N multiplier. So this is the D value, right? Where we put bits 0 to 9 in this register to represent the D value, that 0 to 511. And then the FFLD is registers 12, 13, and 14. And so to write to registers 12, 13, and 14, keep in mind this is a 16-bit register. We need to write to this section. And so to write a 001 to this, that means bits 14, 13 are 0, bit 12 is 1. And so this pound define basically sets bit 12 to 1. Where'd it go? See, 1, 0, 0, 0. And that's in hex. Okay, so that means that it's setting bit 12 to a 1, because the first 0 is the first 4 bits of this register, which is 0 to 3. The next 0 is the next 4 bits, which is 4 to 7. And then the next 0 is the next 4 bits, which is 8 to 11. And then the next bit we have is a 1. See, 1 right there. And that 1 gets stuck in register in bit position 12, which configures this to divide by 2. So that's where we get our what was that called? Pre-scalar. That's where we get this pre-scalar. Whoops. Of divide by 2. Now, so that's reset, reset, and then we'll go to that instruction. Now, this instruction is kind of tricky. We've gone over this. That sets our pre-scalar division, FFLD, and we OR it with D minus 1, right? And so what we're trying to do is build this register, and so this is just a logical OR. So what's going to happen is D minus 1, and the reason that we do D minus 1, remember D is this, FFLN, but if you read the data sheet, it says that these FFLN bits cannot be 0. There will always be 1. That's why it's n plus 1. So since there's already 1 in there, we subtract that off of our D value because in hardware, it's always preloaded with a 1. And really that's because if you think about this, what you're doing is you're telling this to divide by number. So it could be 3, 7, 21, 172, 485. It could be any number, right? And so if you make this number 0, you can't divide by 0. So that's why this is always loaded with a 1. And so what we do is we just subtract that 1 that's preloaded in there off of our D value. And that gives us the remaining D value with the 1 that's already preloaded taken care of. So I hope that makes sense. I'm trying to go through this quickly so it doesn't take a long time for this video, but if you look at this operation, right, this is going to change the value of D because D is going to be ORed with this, right? So it's not it's not like an if DCO bits or D minus 1. This is one function that's going to basically return a value to set equal to UC SCTL2. And so D minus 1 is going to give us 304, and then you OR that with this DCO div bits. But remember, DCO div bits is 100 in hex, which is a pretty big number. So if we do programmer hex 1, 2, 3 decimal 4096, right? So what you're effectively going to do is add D minus 1 to 4096, right? So we're going to get 304, which is 4400. And that's the value, 4400 in decimal, or the hex value 1130 is what we want to load into the register that configures this and this. And so we're building that register, which is, remember, it's right here, ECS2. And this value, if you take this 16-bit binary value, we want it to equal 1130 in hex. Alright, so it's really just building, we're just building that register with this. So now what we do is step over this, or execute that instruction. Alright, so now you can see we've got 4400 up there. Okay, that makes sense. So our register is configured to 1130. Let's go to registers. Let's check this in our special function registers. Where is it? Unified clock system, clock control register 2, 1130. Alright. So if we look at this, here's FFLD, which is this. FFLD. So we're going to divide the output by 2, and then it's going to come up here and get divided by I think it was like 304. What was that? Well, I think it was 304. Yeah, it was 304. It was 305, D plus 1. So D is N really, capital N, so D plus 1. So we're going to divide the DCO frequency by 2, which gives us, at what we're doing, we passed in 20 megahertz. So we're going to divide by 2, that gives us 10 megahertz. And then we're going to divide that by 305 in here. So if we go do that, we got 20. Okay, divide that by 2, 10 million. Divide that by 305. And we get 32,768 and change. And so what this frequency lock loop does is it constantly adjusts the configuration bits for this DCO modulator to keep it as close to this 32,768. So when it starts to drift up, it'll see that this is clocking a little bit out of sync with this, a little bit faster, and it's going to adjust it down. And so you need to study the DCO module to understand how that works. But the frequency lock loop part controls the DCO, digitally controlled oscillator, so that it's basically actively monitored through this division network to match a reference clock. And this is constantly reconfiguring it so that it's most accurate. And so if you use some of the value line series chips, this makes a lot of sense. And some people write their own frequency lock loop control in software for this using the 32,768 kilohertz time or hertz timer on XT1. But basically on the nicer chips, they've incorporated this for you, so you just configure it and let it go. And so this will automatically drive itself at the correct speed to match a reference clock after this DCO passes through these two dividers. That's the idea here. So now this is where you configure some of the DCO, and we'll actually jump down to the F system less than right here. We're going to end up right here. No, actually we're going to end up right here because our system is 20 megahertz, right? So we divide by 1,000. F system is 20,000. It's not less than 20,000. So we'll end up hitting less than 40,000, which is setting our D-core select for the DCO. Now this is the DCO configuration, not the frequency lock loop, but what we're doing is setting this band range of frequencies. So remember, we reset this originally, we cleared it, and now we're going to actually step up and figure out what range we want to be in. I think we're going to end up at 5 or 6. But that's all this is setting the general range, and then it'll get tuned over here by some other bits. But this is a D-core select. It sets the frequency range. It's a pretty wide range, but that's where you start. And so we'll step down to 40. Okay, we'll step in here, we'll set D-core select 6, and we'll verify that 6, it's this range. And if you look at this, this is 10 megahertz, this is 20 megahertz, and 30, 40, 50, all up to 100. And so we set this range because we're at 20 right here, so we're right in the middle of this D-core select. Okay, and so that figures that out. We'll break out of there. Now our D-core select is set to that general range, and our other configuration bits, this is just a fault check to make sure that there aren't any fault flags, and so we jump through that, and that's more DCO oriented stuff. You can check out the DCO to get a little more information on that and some of their examples. Oops. Let's run down to here. Okay, so now we check the mode, and remember the mode, this is a macro that actually sets control for of what clocks are set to. And so as long as we're in the, remember, we only set the D-core select, right? When you use the frequency lock loop, the only thing you really have to set is this D-core select range, because the frequency lock loop does not modify this D-core select D-core select part of the register. And so you have to pick the range that the MSP430 is going to operate in. Once you pick that, the only other two bits that really configure it are the two FFLN, FFLD. Oh no, I'm sorry. DCO mod and the other, there's decore select, DCO, and modulation bits. And if you go to these registers, remember, so from the diagram you can see, so this is the DCO tap selection and the modulation bits, and the FFL controls that. The only thing you really have to set is decore select, because that sets the general range. Once you set the range, let the frequency lock loop configure the DCO and modulation bits, and this will hone in on a specific frequency in that range, and that's controlled up here by this frequency lock loop. See, DCO mod, it controls the DCO. And so that's pretty much all there is to it. Down here you select what your sub-main clock and main clock will be sourced from. Our mode is 1 because our frequency is greater than 16 megahertz. So we're going to set these to the DCO clock, which is going to be, it's going to mean this configuration and this configuration is going to select this DCO clock, not this DCO division clock, which would be half, because our prescaler is 2, remember. So this DCO div is 10 megahertz. This is DCO clock is 20 megahertz, and we're going to use the 20 megahertz. And remember, up top we saved our SCG0 register here, and then cleared that bit. And right now we're going to restore it here. And all this is doing is disabling the frequency lock loop system. It's saving the status of what the status of the FFL was before we'd entered. It clears that bit, which shuts it down, so we can then configure the FFL and the DCO, and all that's configuration. When we're done, we restore the value of that bit. This variable just holds 1 bit. And so we restore the value of this SCGO bit once we're done to return back to the state the system was at before we went and configured it. And so that's pretty much it. That's this function. Hope that was helpful. If it was, and you'd like any videos or write-ups on anything else, let me know. If I have time, I'll put some out. But I thought this was kind of confusing, and so hopefully it'll help some people out. And all right, until next time.